What problem does the proposed NEA neighbor speculative decoding nest method aim to address in language models?
The proposed NEA neighbor speculative decoding nest method aims to address the problem of hallucination in language models, particularly when dealing with long-tail knowledge that is less represented in their training data. NEST is designed to enhance evidence-based and situated reasoning with large language models, LLMs, by incorporating real-world text spans of arbitrary length into the generations of an off-the-shelf LM. This approach leads to improved quality and latency in content generation. NEST extends the standard 10-number-1-0 approach by conducting an additional passage retrieval step at the beginning to limit the need to store and search over all tokens in the corpus, offering a balanced trade-off between search accuracy and efficiency. By dynamically selecting spans, interpolating output probabilities, and implementing relaxed speculative decoding, NEST aims to provide more accurate and reliable content generation while improving efficiency in long-form generation tasks.
How does the proposed NEA neighbor speculative decoding nest method work step by step?
The proposed NEA neighbor speculative decoding nest method works in three main steps. 1. Content-based interpolation. NEST uses a relative retrieval connance (RRC) score to measure the uncertainty of the token retriever. This score is used as the interpolation coefficient of the output probability mixture. It allows for dynamic adaptation of the language model's output to different downstream tasks through flexible interpolation with the token retrieval results. 2. Dynamic span selection, inspired by the copy generator, COG. NEST not only selects the best token predicted by the mixture probability, but also extends to the span containing tokens from the corpus when the token retrieval connance exceeds a predefined threshold. This ensures coherence by extending the context of the current sampled token. 3. Relaxed speculative decoding. NEST uses a relaxed version of speculative decoding to control the adaptive length of spans. It revises the proposed n-gram by upper bounding the acceptance probability, allowing for spans with adaptive lengths. If a token is rejected, all tokens from that point onwards are removed, and a new token is selected from the distribution without going through the span selection process again. This procedure can be parallelized, improving efficiency and maintaining or even accelerating generation speed.
What are the theoretical or practical benefits of using NEA neighbor speculative decoding (NEST) over existing retrieval augmented language models?
The theoretical and practical benefits of using NEA neighbor speculative decoding (NEST) over existing retrieval augmented language models include improved quality and latency in content generation tasks. NEST extends the standard 10-number-1-0 approach by incorporating real-world text spans of arbitrary length into the generations of a pre-trained language model, leading to enhanced performance in various free-form generation tasks such as question answering, text completion, and factuality-aware generation. NEST demonstrates superior performance compared to base language models and the standard 10-number-1-0 under a zero-shot setting, showcasing its effectiveness in improving content generation quality. Additionally, NEST provides better attribution directly at a span level, ensuring accurate and reliable information retrieval from the corpus, which enhances the credibility of the generated content. Furthermore, NEST significantly improves the efficiency of long-form generation by generating multiple tokens at each time step, resulting in a speed-up in inference time without compromising attribution or fluency. Overall, NEST offers a balanced trade-off between search accuracy and efficiency, dynamic adaptation to downstream tasks through content interpolation, and enhanced generation quality and attribution, making it a valuable advancement in the field of retrieval-augmented language modeling.
How is the performance of NEA neighbor speculative decoding (NEST) validated in the paper?
The performance of NEA neighbor speculative decoding (NEST) is validated in the paper through a series of experiments on various tasks, including text completion, question answering, fact verification, and closed set tasks. The evaluation is done using the Llama 2 chat models of different sizes, under a zero-shot setting, where few-shot demonstrations are removed from the instructions to simulate realistic model usage. The experiments compare NEST with base language models, LMs, 10(1)0NNLM and in-context retrieval augmentation, RAW, on tasks like Wikitext 103, Pile of Law, Natural Questions, Trivia QA, Hotpot QA, Med MCQA, Biography Generation, Truthful QA, and Massive Multitask Language Understanding, MMLU. Metrics such as perplexity, Rouge scores, FACTSCORE, hit at 1, and macro accuracy are used to assess the performance of NEST in generating accurate, fluent, and attributed content across different domains. The results show that NEST outperforms base LMs and 10(1)0NNLM on most tasks, demonstrating superior performance in terms of quality, latency, and attribution. Additionally, the paper provides a detailed analysis of the latency-accuracy trade-off, attribution at a span level, and qualitative results to further validate the effectiveness of NEST in enhancing language model performance.
What specific results were achieved with the NEA Neighbor speculative decoding, NEST method in text completion and question answering tasks?
NEST achieved specific results in text completion and question answering tasks. In text completion tasks on Wikitext 103, NEST demonstrated superior performance with the lowest complexity compared to other methods. For question answering tasks on knowledge-intensive datasets like Natural Questions NQ, Trivia QA TQA, Hotpot QA HQA, and Med MCQA MQA, NEST tended to work better for smaller models 7B and 13B, and outperformed base LMs in general. The combination of NEST with retrieval augmentation, raw NEST, showed improved performance for the 70B model in fact verification tasks. Additionally, NEST consistently outperformed base LMs and in-context retrieval augmentation methods in truthful QA, showcasing its effectiveness in handling adversarial datasets. Overall, NEST provided better attribution and latency, demonstrating its capability to enhance text completion and question answering tasks across various domains and model sizes.
What limitations are mentioned for the NEA Neighbor speculative decoding, NEST method in the paper?
The limitations mentioned for the NEA Neighbor speculative decoding, NEST method in the paper include the potential for factual errors in the output depending on the accuracy of the first stage passage retrieval and the second stage token retrieval. Additionally, as a plug-and-play method, NEST aims to be a flexible solution that can combine different large language models, LLMs, and data stores in zero and few-shot settings, but without further fine-tuning, the integrated system may not be optimal. Furthermore, the paper notes that semi-parametric LMs like NEST may not enhance in-context learning, as the prompt's demonstrations are unlikely to align with contexts found in the database. Preliminary experiments suggest that current neural retrievers may struggle to process in-context few-shot information effectively, potentially requiring techniques like query reformulation for parsing the demonstrations.